Another important topic that we'd like to cover is naming of compounds. You need to know, go from the name of a compound to the formula to be able to work problems in Gen Chem 2. So an important concept that we covered back in Gen Chem 1 was metals, nonmetals, and metalloids. Okay, generally on the periodic table, there is a staircase that starts between boron and aluminum and goes down all the way down the periodic table. We said that those things are to the left of that staircase were called metals. Those things to the right were nonmetals. Those things touching it were metalloids. This concept is very important to us because we're going to use that to determine bond types. Okay, if we talk about metals and nonmetals combining, we refer to those as ionic compounds, and those things that were nonmetal arrangements, we refer to them as covalent or molecular compounds. Now, this is a generality. Now, and realistically, you may recall back in Gen Chem 1 talking about change in electronegativity, where we said if the change in electronegativity between two atoms was less than 0.5, then we said that was going to be a covalent bond, and it was going to be a nonpolar covalent bond. If it was between 0.5 and 1.8, we said that was going to be a covalent bond, but it was going to be a polar bond. If it was greater than 1.8 electronegativity difference, we refer to that as an ionic bond. Okay, but we don't walk around knowing electronegativity, so we tend to use the generality with the periodic table. We're basically saying metals, nonmetals, ionic bond, nonmetal, covalent bond. And we use that information to decide to name things as well as how to name compounds. We also use that to determine solubility and how things are going to dissociate or ionize in solution as well. We have some terminology associated with chemical formulas that depend on the bond type as to what terminology we use. So we're going to talk about molecular and ionic substances. So let's define what we refer to as a molecular substance. That's a substance that involves covalent bonding. That's basically the sharing of electrons between atoms. Typically, we refer to a nonmetal arrangement. What you have is a pair of electrons that are being shared between two atoms. That's a covalent bond. They're sharing electrons between them. Ionic substance involves a transfer of electrons between atoms. Basically, that bond is an attraction between charged particles. Typically, we're talking about a metal-nonmetal arrangement, or we should say more realistically, charged particles, because polyatomic ions would also have that attraction between charged particles. So that attraction between the positive and negative is that ionic bond. One species gives up the electron, becomes positively charged. The other one takes on the electron, negatively charged, and that attraction of charges is that ionic bond. So for molecular substance, let's talk about some terminologies that we use. One is a molecule. A molecule is a definite group of atoms that are chemically bonded together through sharing of electrons. Basically, we have a covalent bond, generally nonmetal. Also realize that hydrogen, even though it's on the left side of the periodic table, is part of the nonmetals. So if I talk about water, okay, H2O, that's covalently bonded, that's referred to as a molecule. Okay, that's a molecule because we're talking about covalently bonded atoms. A molecular substance is a substance that is composed of molecules, all of which are alike. So when I talk about water, there's billions and billions of molecules of water that make up the molecular substance of water. A molecular formula gives you the exact number of atoms or elements in a molecule. In this case, C2H6O. That tells me the atoms involved in that molecule of ethanol. Okay, that's a molecular formula. Refer to that as a molecular formula when we're talking about covalent bonded species. However, there is another type of formula that we tend to use. It's called the structural formula. This shows how the atoms are bonded to one another in a molecule. It gives us more information. Gen Chem, we tend to use molecular formulas. You get to organic chemistry, they're going to be more structural formulas, so you got to be familiar with them. Look at this example here. We got CH3, CH2OH. Look, notice there's 2 carbons, 6 hydrogens, and 1 oxygen. That is the same formula as the molecular formula is given. That is also ethanol. Both of those are ethanol. Just one gives us more information. Okay, so basically the CH3CH2OH is telling me how the molecules put together. I have a carbon with 3 hydrogens around it, attached to another carbon which has 2 hydrogens, attached to an oxygen, attached to an hydrogen. And that tells me more information about how this is put together. As I said, in organic chemistry, things will tend to be more written in structural formulas than we do in our gen chemistry. Okay, ionic substances, those things that are based on the transfer of electrons, basically attraction of charged particles. Okay, so we're going to discuss next. Although many substances are molecular, others are composed of ions, in other words, charged particles. There's a transfer of electrons based on ionic bonding, generally metal, non-metal, but we're talking about charged particles. Those things with a large electronegativity difference between it. Or charged particles, or ions, okay, that are attracted. An ion is an electrically charged particle obtained from an atom or chemically bonded group of atoms by adding or removing electrons. Basically, something gives up an electron, something else takes it on, and they become charged particles. They have an excess of protons versus electrons, or vice versa. Example, sodium, elemental state of sodium, could give up an electron and basically become positively charged. When it does so, and the chlorine takes on that electron, then chlorine has more electrons than it had protons, therefore it becomes negatively charged. These are ions. Sodium plus and Cl minus are ions, electrically charged particles. Sodium chloride is a substance made up of those ions. There's an attraction between the sodium and the chlorine for the plus and minus. For ionic substances, the formula of an ionic compound is written by giving the smallest possible whole number ratio of different ions in the substance. This is different from molecular formulas. Molecular formulas do not have to be the smallest whole number ratio. However, ionic substances, they do. A formula is compared to what we refer to as molecular formula for covalent compounds, molecular compounds. The formula unit of a substance is a group of atoms or ions explicitly symbolized by its formula. So that's in comparison to the molecules in the molecular substance. We refer to ionic substances as formula units. So I wouldn't say sodium chloride is a molecule. I would refer to sodium chloride as a formula unit because it's ionic bonding. Refer to water as a molecule because it's covalently bonded. So, going over what we talked about terminology, we can see, talked about covalent bonding, okay, that's a sharing of electrons as compared to ionic bonding, which is the transfer of electrons, which is basically attraction of charged particles. Typically for covalent bonding, it's a non-metal arrangement. Ionic bonding is a metal-non-metal, or we also could say charged ions as well. We refer to covalently bonded species as molecules. Refer to ionically bonded species as formula units. Refer to those substances combined as molecular substances for covalent bonds. And ionic bonds we refer to as ionic substances. That repeating unit in covalent bonded substances we refer to as molecular formula. And for the ionic bonding we refer to that as formula. Okay. Recall that for covalent bonding there's a sharing of electrons. Ionic bonding, we're talking about an attraction of charged particles. We'll give names to those charged particles. So let's just discuss that for ionic substances. When an atom gains extra electrons, it becomes negatively charged. It has more electrons than it has protons. We refer to that as an anion. Okay, we refer to that as an anion. An atom that loses electrons becomes a positively charged ion. That means I have more protons than I have electrons. Okay, we refer to that as a cation. Okay, we refer to that as a cation. So Cl minus as an anion and sodium plus as a cation. When we put the anion and the cation together, we refer to that as a ionic compound. Okay? Ionic compound is a compound composed of cations and anions. So when we put the two together, then we basically have ionic compound. Notice we do not put the charges when we put the two species together. Alright, if we understand these terminologies, we should be able to answer some questions right now for the next couple of species. What I'm looking for is if it's an ionic or molecular compound, as we refer to that as a formula unit or a molecule. Does it have ionic or covalent bondings involved? Let's look at sodium chloride. Okay. What kind of bonding are we talking about there? Well, we're talking about a metal and a non-metal bonding, right? So if that's the case, then we're talking about ionic bonds. If it's an ionic bond, then would I refer to that as ionic substance or molecular substance? It would be ionic substance. And when I refer to sodium chloride as a formula unit or a molecule, since it's ionic bonding, it will be referred to as a formula unit. Let's look at calcium bromide. Okay, what kind of binding do we have there? Well, once again, we got a metal, non-metal. Now notice there's two bromines to every one calcium. That gets into the charges. We need that whole charge to be neutral. Calcium's a 2+, bromine's a -1, so it takes two of those to balance that charge to 0. But it has ionic bonding. Since it has ionic bonding, we refer to that as an ionic compound. And once again, I'll refer to it as a formula unit. Na2SO4, sodium sulfate. Okay. Well, what you have is a sodium ion, which is Na+, and sulfate, which is a polyatomic ion, which is a 2-. That's being attracted to each other and held together to form the compound. So you have ionic bonding between the sodium and the sulfate. However, I also have covalent bonding that is going on in the SO4, because that's non-metal arrangement between that SO4 2-. Okay, so I have covalent bonding here, and then I have ionic bonding between the species. So I have both bonding involved in this particular compound. But since the actual cation and anion together is ionic bonding, we refer to this as ionic substance. And I was also referred to it as a formula unit. So it's ionic substance, it's formula unit, and it has ionic and covalent bonds. Last example, CO2. Okay, carbon dioxide. Okay, talking about a non-metal. Therefore, what you have there is a covalent bond. Since it's a covalent bond, we refer to that as a molecular substance. And since it's a molecular substance, we refer to that as a molecule. Molecular substance, the molecule, covalent bonding. Now notice when I said the names, I said carbon dioxide, and for calcium Br2, I said calcium bromide. There's a difference in name and procedure between the species. Since there's ionic bonding in the calcium bromide, I don't have to use prefixes. Yet in the carbon dioxide, I had to use the di because of the fact that it was covalent bonding. Okay, so the difference of bonding dictates whether I use the prefixes or not, which we'll talk more about in the next couple of slides. Another important property that has to do with bonding between ionic versus covalent is how ionic and molecular substances dissolve in water. Okay, this is an important thing to realize because later on, as we get to writing reactions and now chemistry, later chapters, we need to decide how things are going to break up or not. Okay? Many ionic compounds, meaning your ionic bond, metal, nonmetal, charged ions, dissociate into independent ions when dissolved in water. So if you have a species which is soluble, and that solubility is based on how large the species is, if it's a low charge ion, etc. Those tend to be more soluble, okay, things that are larger and lower charge. But all that's built into the solubility rules. Okay, so if you learn the solubility rules and you learn that something is a soluble salt, say sodium chloride, we say it's a soluble salt, then what happens is when we place that in water, it ionizes. Okay, ionic bond will break, that charges between that plus and minus separate, and we end up getting sodium ions and chlorine ions in water. Okay, that aqueous, AQ, means that basically it's surrounded by water molecules. Since sodium is a plus, it's attracted to the negative end of the oxygen. You might recall that when you draw water, there's dipoles. There's a dipole plus on the hydrogen and a dipole negative on the oxygen. Well, there's going to be attraction between that plus and the oxygen. So oxygen is going to surround the sodium ions. Okay, the opposite happens in the chlorine. Basically, the hydrogens will be attracted toward that hydrogen. That chlorine, because of that excess plus charge on that hydrogen. And that's what we mean when we're saying something's aqueous. So basically, soluble ionic compounds dissociate 100%. So if they're soluble, okay, we say they break up 100% into the ions. Since they're ions, we refer to them as strong electrolytes. There's charged particles there in the solution. And not all ionic compounds are soluble. Okay, only those ones that we said are soluble based on the solubility rules break up 100%. Now, when we say something's soluble, you got to realize that it's not infinity. Okay, now say sodium chloride, the solubility of it is about 36 grams of sodium chloride per every 100 milliliters of water. So that means once I get more than 36 grams, it's going to be a saturated solution and no more will go in solution. So it's not infinity. I can't put a truckload of salt on 100 milliliters of water. There's some limitation, but it's a large amount before it reaches that saturation point. On the same point, when I say something's insoluble, doesn't mean it's 100% insoluble. Okay, there's still some that's going to be in solution, which we're going to talk about those calculations later on as we go in the semester. So soluble doesn't mean infinity, and insoluble doesn't mean zero. Okay, there'll still be some that will be in solution. All right, most molecular, covalently bonded, non-metal compounds dissolve in water, but do not dissociate into ions, with the exception of the acids. So when we're talking molecular substances, that covalent bond will not break, okay, when it dissolves in water. So it is soluble. So it does go and dissolve in water. Sucrose, your sugars, glucose, and all that dissolves in water. But when it dissolves, okay, and we're looking at non-metal arrangements here, which is happening here in our glucose, okay, when I stick it in water, it dissolves, but it stays as a whole. Okay, it stays as a whole molecule. It doesn't break into 6 carbons, 12 hydrogens, and 6 oxygens. It stays as a whole molecule. So it dissolves, but it does not ionize. These compounds are referred to as non-electrolytes, okay, because there's no charged particles. Soluble, but no ions formed. So if you understand what we're talking about with bonding here, then we should be able to look at this next example. Question is, how would the sodium sulfate dissolve? Okay, if I put sodium sulfate, how would it dissolve in water? All right, well, you got to look at the bonding there. We've got sodium sulfate, so you got sodium and sulfate. That's an ionic bond between those ions. SO4 2- is a covalently bonded polyatomic ion. So since it's that, it will not dissolve. Okay, so that SO4 2- will stay as a whole. So in essence, what happens is that ionic bond will break, which will leave me with two sodium ions, okay, two individual sodium ions, and one sulfate ion. Okay, so that knowing your bonding allows me to know that it's going to break and give me my sodium ions and my sulfate ions. This sulfate will stay whole because of the fact that it's covalently bonded. Okay, most ionic compounds contain a metal and non-metal, or we should say charged particles, because you get something like the sulfate that we discussed. Okay. You name an ionic compound by giving the name of the cation first, followed by the name of the anion. Okay, so some examples. Okay, sodium chloride, potassium bromide, calcium iodide. Notice something about the naming here for these ionic compounds. The name of the first species, the cation, okay, the cation, we name the element just as the name of it is. Okay, sodium, potassium, calcium. We did not make any changes. That's the name of the element. However, in the anion, the second part, what we did was we changed the ending to IDE. Okay, we took the root of the word chlorine and we took the INE and changed it to IDE. That's how we name our compounds, ionic compounds. Fairly simple. A monatomic ion is an ion found in a single atom. So we have names for all the monatomic ions. Typically, it's the name of the element. Okay, when we're talking about the cations and we talk about anions, we have the IDE ending on it. Important thing to realize is charges. When we go to put formulas together, I need to know what are the charges on something, know how many of my anions I need for how many cations, etc. And also when we're going from naming compounds, we need to know what the charges when we start talking about some certain metals. Okay? So let's talk about the rules for predicting charges on monatomic ions. Most of the main group metals form cations with a charge equal to their group number. The charge on the monatomic anion for a nonmetal equals the group number minus 8. Okay, so typically your anions is equal to that group number minus 8. And we're talking about the Roman numerals, not the Arabic numbers on the periodic tables. Most transition elements form more than one ion, each with a different charge. So exceptions of the transition metals would be cadmium 2+, zinc 2+, and silver plus. Now there is a rare version of silver 2, which may come up and they give you, say that's one with a variable oxidation state as well, but it's a rare occasion. Now this is the rules. A little easy if I just do it based on the periodic table. First off, I have some other important elements with variable charges that we need to take account for too. Lead, lead 4, lead 2, tin 4, tin 2, arsenic 5, arsenic 3, antimony 5, antimony 3. These are other variable oxidation states you need to be familiar with when you go to name compounds. As I said, I want to look at the periodic table. I can look at the periodic table and make some ideas about what the charge is on species. Let's look at that first column, okay, this group of elements right here. Okay, what's happening there is they all have the same outer shell of electrons. Okay, they all have one electron in the outer shell, and everything's trying to get to an octet, which means they want 8 electrons in the outer shell. So the question comes up: will it be easier for those species to lose 1 electron and get to the outer shell to the next level, or gain 7 electrons to get 8 into the outer shell? Well, obviously it'd be easier to lose 1 than gain 7. And that's why they tend to do that in that first column. And what we tend to do is that everything in that first column tends to be +1. Okay, have a +1 charge. Second column, the same thing's happening, except it's easier to lose 2 than gain 6. So in that second column, it also has a +2 charge. All those species in that second column tend to have a +2. Now we're going to skip the middle there and jump all the way over to the 13 or Roman numeral 3a. Same thing. I had 3 electrons, easier to lose 3 than gain 5, so those species tend to be +3. Next column, 4a, tend to be +4. But right now we're at a halfway there point. So it could be +4, it could be -4. So what we're going to do is change gears now, go all the way over to the right, to the noble gases, 8a. Now they have 8 electrons in the outer shell, so they're already half full. So they don't want to lose or gain any. So they tend to have a 0 charge. We go over 1, fluorine, chlorine, bromine. We got 7 electrons in the outer shell. Easier to gain 1 than lose 7. So they tend to have a -1 charge. Go over to the oxygen, sulfur, etc. Tend to have a -2 charge. Nitrogen, phosphorus, -3 charge. And if we wanted, we go one more over to -4. So the question comes up, well, what's going to decide over here whether they're -4 + 4, -3 + 3, since they in that general area where it's close? Well, it's going to be what it's connected to. The thing that is more electronegative will tend to be an anion. The thing that is more electropositive will tend to be a cation. So it kind of depends what it's part of to decide what charge it's going to be. Then we have our transition metals, which tend to be variable. If you had to guess at a charge, then +2 is a reasonable guess, but it's variable and it depends on what it's connected with. And that's why we have to say, now name the Roman numeral of what charge it is, for we know how to put back the formula when we try to write the formula. So monoatomic cations are named after the element. So example, Al3+, that's aluminum. We just simply call it aluminum ion. And we put the ion on it when it's a charged particle. Now when we put that together with a with an anion, then we drop the ion and just use the aluminum part. If there's more than one cation of an element, then we use Roman numerals in parentheses denoting the charge. I have to tell the reader what the charge is, otherwise we can't figure it out to write the formula. This mostly occurs with the transition elements, but also those few elements, the lead, antimony, arsenic that I told you about as well. So sodium is always a +1, so I don't have to put a Roman numeral, but this is simply a sodium ion. Calcium is always +2, so this is simply calcium ion. I don't have to put any Roman numerals. However, for iron, there's 2 different states. There's iron 2 and iron 3. So if I do not put the Roman numeral and I just put iron, I do not know if it's charge 2 or charge 3. So I need to put that into my name. So for iron 2 ion and iron 3 ion, I must put that Roman numeral. That Roman numeral is telling me the charge on that species. That Roman numeral is telling me the charge on that species. Now, there's an older name that we tend to use instead of Roman numerals. We use the ending to change to tell us the higher or lower oxidation state. So it's something you got to be familiar with. The higher oxidation state name, we usually use the Latin name and we put ic on the end of it. And for the lower oxidation state, we'd use us, with the Latin name. So if we go back to the iron example, instead of writing it as iron 3, we could write it as ferric ion, ferric ion. The ic goes with the higher oxidation state of +3. I could do it right iron 2 as ferrous ion. Iron 2 is the low oxidation state, so I use ferrous ion. Copper is another example. I could write it cupric ion, copper 2, or cuprous ion, copper 1. Mercury, Ag2+, mercuric ion, or Ag subscript 2, 2+, mercurous ion. Now that's the one that sometimes tends to confuse people. Okay, I realize I got two mercuries. This is a cation polyatomic ion. I have two mercuries and the total charge is 2 plus. That basically means that each one of these mercuries theoretically is a plus 1. Okay, so that's mercury 1. Okay, that's mercury 1. Ion. Okay, in fact, because that mercury is a plus 1 inside, that subscript 2 just telling me how many's there. The names of the monatomic anions use the stem of their name of the element followed by the suffix IDE. So if you're talking about bromine, okay, all we do is you take that INE and change it to IDE, the bromide ion. Okay, it would be for my Br minus. Now do recall that we had those other elements we talked about, lead, tin, etc. They're also, you're going to be familiar with them using the older name as well, with the ic and us, with the higher oxidation state and the lower oxidation state. Okay. Another thing that we have to do is be able to put formulas together from the name. So let's talk about formulas of ionic compounds. Now, recall that they're written by the smallest possible whole number ratio. The smallest possible whole number ratio, which is not the same for molecular substances. They do not have to be. But for ionic compounds, they are. Okay, the smallest possible whole number ratio of different ions. So some people tend to do is just cross multiply to figure out how many atoms you need for each one, which is fine, but you got to remember it has to be smallest possible whole number ratio. Let's look at the first one, sodium chloride. Okay, you got to figure out what the ions there are. Okay, so you got sodium, which is plus 1, and chlorine, which is minus 1. I need this total charge, these pluses and minuses, when I add them up to equal to 0. So I'm going to have to put subscripts down next to each atom to get it to equal to 0. In this case, I got plus 1, minus 1. Therefore, all I got to do is put those together, and I have my compound, which is sodium chloride. Okay, no charge is written. Iron 3 sulfate. Okay, you got to realize what that 3 is telling me is the charge on iron. It's not telling me the subscript of iron. It's not telling me anything about sulfate. It's telling me the charge on iron. Okay, so that's where this 3 plus is coming from. Okay, from that iron 3. Then I got to write my polyatomic ion, sulfate. That's something you're going to have to memorize. Okay, it's SO4 2 minus. I need this total charge to be the same. So what I'm saying is you can cross multiply to get that. Okay, I need a total of equals 0. So I got 2, okay, 3s and 3 2s, okay, which basically tells me I have 2 times 3 plus, which is 6, and 3 times 2 minus, which is minus 6, which, you add that up, that's equal to 0. Okay? So basically, I'm trying to get this to balance out, so I'm going to say I need 2 iron 3s and 3 of the sulfates, okay, which means I have now, my formula is Fe subscript 2, open parentheses SO4, close parentheses subscript 3. That gives me 3 sulfates at minus 2, total of minus 6, 2 iron 3s, that's plus 6, add that up, that's 0. Okay, you need to balance it out. Let's look at chromium 3 oxide. Once again, that 3 is telling me the charge. That's telling me the charge on the chromium. So that's giving me my charge on that chromium. Okay, chromium 3 oxide. Need to balance this out. Okay, so in this case, I'll cross multiply, which then gives me chromium 2, O3. Calcium nitrate. I got calcium 2 plus, nitrate minus 1. Need the charges to balance. I got 2 pluses on the cation, a minus 1 on the anion, which means I need 2 nitrates. Calcium, open parentheses, NO3, close parentheses, subscript 2. The parentheses are important, okay? I need to make sure I put them because it's the whole polyatomic ion. I need 2 of them. Sodium phosphate. Sodium is a plus 1. Phosphate has a minus 3. So I need to balance this out. So I'm going to need 3 pluses to balance out those 3 minuses. Therefore, I get Na subscript 3, PO4. Strontium oxide. Okay, I got a 2 plus and a 2 minus. Therefore, all I got to do is write SRO. This is one of those examples. If you cross multiplied, you would have SR2O2. That's something that's not your smallest possible whole number ratio. It's divisible by 2. You would have to divide by 2 to get it down to its lowest whole number ratio. That's the one drawback of the cross multiplying. You got to make sure you get it to your smallest possible whole number ratio. Okay, now let's see if we can name some compounds. Now, one thing I want you to keep in mind as you go through this is that, yes, we only did ionic compounds, so you only know how to name those right now. But you got to remember, things are going to be mixed up all over the place. So you want to make sure you think about how to name the compound each time. So as you go through, you want to look at the bonding. Okay, it's ionic bonding, and we know how we name that. When we get to molecular covalent bonding, you know how you name that. So you want to think about that. Okay, so let's look at NAF. Okay, what type of bonding is that? That's ionic bonding. Therefore, we're going to name the cation and then the anion. There'll be no prefixes involved because this is ionic bonding. So we've got to figure out what is Na. Na is sodium. And then what is F? Okay, well, it's the anion, so I got to change the ending of the fluorine to fluoride, which gets me, in this case, sodium fluoride. Okay. Notice there's no charges. I don't have to put Roman numerals or anything because sodium is always +1. Also notice that I have UO in black there to emphasize the spelling of fluoride. When you go to input these answers into the homework system, you got to make sure you spell things correctly, and a common misspelling is fluoride. It's U before O. Lithium chloride. I want to take that name and get it into the formula. So you got to figure out the charges on the species. Well, lithium, okay, it's in that first column, so lithium is a +1. Chlorine's in that second to last one, so that one's going to tend to be a -1. So I need to put that plus and that minus together into a formula, which in this case would be LiCl. MgO. Got to name that. So I got magnesium as Mg. Okay, I don't have to put any Roman numerals because that's always +2, so I don't have to put the Roman numerals. And then I have O, which is the oxygen, so we change that ending since it's the anion to IDE, which means I get magnesium oxide. The next one, MnBr2. Well, Mn is one of those transition metals, so I'm going to have to say what to charge on that, so I'm going to have to figure it out. Bromine's always -1, so I can do a little arithmetic if I want to figure this out. I know I got manganese plus 2 bromines, and that's always a -1, and that whole thing has to equal a 0 charge. Well, mathematically, that means Mn is equal to 0 plus 2, which means +2. So this manganese has a 2+ charge. I need to balance that out. Okay, I can do a little arithmetic or see it in my head. I got Mn and I got Br -1. I got 2 of them, -2. I got to be +2 in the manganese, the whole thing to equal 0. So then I need to put that into my answer. Manganese, Roman numeral 2 for the metal. And then I got to name the anion, which in this case, bromine, change the ending, IDE, bromide. Manganese to bromide. Cobalt 3 oxide. Got to recall that Roman numeral is telling me the charge on cobalt. So I got cobalt with a 3+. Oxide, which tends to be your O2-, need to put that together so you can cross multiply. You get your cobalt 2, subscript 2, O3. Now you got to realize all the elements, all first letter capitalized, the second letter small. Okay, so putting it as a capital CO here would be different. That's going to add another oxygen. You need the symbol for cobalt, which is a capital C, small o. Okay, I have another one, copper 2 chloride or cupric chloride. Okay, got to remember that Roman numeral 2 is telling me my copper, which is copper 2. And then I have chloride, which is a -1. Okay, need to balance that out, which means I get CuCl2. Once again, all these ones we worked on, you need to think about the bonding there. Okay, what type of bonding was each and every one of these examples? These were all ionic bonding. Okay, metal, non-metal. Okay, keep that in mind because eventually we're going to mix things up and you're going to have the covalent. You're going to make sure you're making the right decisions of when to use prefixes and when not to use prefixes. It's all based on the bonding. Another part of ionic compounds that's important would be the polyatomic ions. Polyatomic ion is an ion consisting of two or more atoms chemically bonded together and carrying a net electrical charge. Okay, example, sulfate, SO4, 2 minus. That SO4, that whole thing has a 2 minus charge. There's tables in books that list some common polyatomic ions. I'm going to put on the next table a list that you should be familiar with. That's not all of them, but there's some of them that you should have in your top of your head. Most of them are oxyanions. That means it consists of oxygen with another element being the central element. Okay, examples. Nitrate and sulfate here. And the reason I'm putting these up is I want you to look at them to see the difference and try to help you in memorizing. Okay, what do you notice is the difference between NO3 minus and NO2 minus? Okay, well, they're the same charge, got the same number of nitrogens. The major difference is the number of oxygens. So if you memorize the 8s, okay, is NO3 minus, I know an nitrite is 1 less oxygen. Okay, same thing happening in the sulfate. Okay, I know my 8 is SO4 minus, SO4 2 minus. I memorize that. I know if I lose an oxygen, it goes to sulfite. Okay, most groups are 8 and 8 and they differ by an oxygen. Okay, so you memorize them and you know if you lose an oxygen, you go down to the ites. Now there's several groups. The manganese, bromine, chlorine, and iodine that go a little further. They got 2 extra groups. You got per-8, 8-ite, hyper-ite. Okay, basically say ClO4 minus. Okay, that's referred to as your perchlorate. Ion. Okay, when I lose 1 oxygen, I go down to ClO3 minus. Well, I'll drop the per, but I keep the chlorate. Then it'd be chlorate ion. Okay, once I lose another oxygen, ClO2, then I change it from 8 to ite, which is chlorite ion. And I'll lose one more, ClO minus. That's when I add a prefix. It'd be hypochlorite so I still have the ite ion. Okay, and that happens with the manganese, your bromine, your chlorine, and your iodine. Here's your list of polyatomics you should be familiar with. Most of them are anions. There's only a couple of cations, one being ammonia, that's an important one, and mercurous or mercury 1. Okay, here's that set of perchlorate, chlorate, chlorite, hypochlorite. Okay, most things, polyatomic ions, are named with endings that are not IDE. Okay, IDE tends to be your elemental species. So if you see IDE, most likely it's an element. Now there are a couple of polyatomic ions, but you memorize those and kind of get familiar with those. They don't look like single atoms, okay, single elements. Okay, example, here's an IDE, which is hydroxide. Okay, hydrogen and oxygen, that's not an element. Okay, that's actually you can tell that looks like a compound. Okay, so you basically got hydrogen and oxygen together, then you're talking about a polyatomic ion, hydroxide. Cyanide, okay, it's another example. Alzide, another example. But most things with IDE are your elements, just to give you an idea as you're trying to look at things. Other things to keep in mind, adding hydrogens, okay, for example, we've got carbonate. I add a hydrogen, remember I'm adding in that hydrogen has a plus charge on there, so if I'm adding a plus charge, then that charge is going to go down by 1. So then I have hydrogen carbonate, I have HCl3 with a minus charge, a single minus charge. Older naming of that is bicarbonate ion. Similar would be phosphate. Okay, PO4 3 minus. Okay, down at the bottom you see I got dihydrogen phosphate, got 2 hydrogens on it, and notice the charge went from a 3 minus to a minus 1 because I added 2 hydrogens on it. Another important one to realize is acetate. A lot of times it's written C2H3O2 minus as its molecular formula, But sometimes I tend to write it as a structural formula, so you got to be familiar with me if I write it this way, CH3COO minus. That's the same thing, okay, as an acetate ion. It's just a structural formula. But these are the ones you should be familiar with as you go through and keep these in your head as you work problems. Okay, let's go to naming some polyatomic ions. Let's look at SnSO4. Once again, I want you to think about the bonding. We're talking about ionic bonding here. So we're going to go by those rules. There's no prefixes. I got to figure out what Sn is. Sn is 10. But that's one of the ones that have variable oxidation state. Remember I told you 10-2 and 10-4. So let's see which one it is. Well, I got to know what SO4 is. SO4 memorized is sulfate with a 2- charge on it. That means that that 10 has to have a 2+. So I can name this one of two ways. 10-2 sulfate, that Roman numeral 2 telling me the charge on 10, or stannous sulfate, being in the lower oxidation state. Sodium sulfite. So now I got to put these together. So I have sodium, which has a +1 charge. And I have sulfite, which is SO3 with a 2- charge. Okay. So I need to put those together. So I'm going to go ahead and cross multiply. Then I want to have Na2SO3. Okay, now I want to name Ca, open parentheses, ClO, close parentheses, subscript 2. Well, Ca is calcium. It's always a +2, so I don't need Roman numeral. But then I got to figure out what ClO is. Okay, and that goes by the polyatomic ions, which was the hypochlorite ion. So putting that together, calcium hypochlorite. Barium hydroxide. Okay, I got to remember what barium is barium 2+. Hydroxide was OH-. Okay, got to put those together. We want that to cancel out, which means I'm going to need 2 hydroxides. Which gives me Ba, open parentheses, OH, subscript, close parentheses, subscript 2. Ba, open parentheses, OH, close parentheses, subscript 2. Potassium perchlorate. Okay, I got potassium perchlorate, which is ClO4-. Okay, I got to put those together with +1 -1. That's just ClO4. Cr2, open parentheses, SO4, close parentheses, subscript 3. Okay. Once again, as we go through these, we should be keeping in mind what type of bonding is holding these together. All these ones we've been doing so far are all what type of bonding? Ionic bonding. Okay, they're all ionic, so there's no prefixes involved. Okay, so everything's been ionic bonding so far. Chromium is one of those transition metals, so I need to figure out what the charge is on that chromium. So I know sulfate is a 2-. Okay, I know sulfate is a 2-. Okay, so I got 3 -2s, that's a -6. And I got 2 chromiums. So what charge has the chromium have to be for this to balance out? I need a +6 to balance it out, which means that chromium has to be a 3+. So I need to put that in my name, which means I would name this chromium 3, and then name the polyatomic ion, which is sulfate. Okay, remember that Roman numeral 3 is telling me the charge on that metal. Magnesium nitride. Okay, so you got to remember what magnesium is. Well, that's always going to be a +2. And then what is nitride? Okay. Now, all we've been doing is polyatomic ions, so your tendency might be here to start throwing in an NO3- for the nitrates and nitrites. I want you to think about things. Remember I said IDE looks like the element, most likely an element, right? Remember the NO3- is nitrates, nitrites. Okay, so in this case, this is not a polyatomic ion. This is just nitrogen, okay, with its charge, which is going to be a 3-. Put those together. Mg3N2. Fe3, open parentheses, PO4, close parentheses, subscript 2. What type of bonding am I looking at here? Same as all the ones we've been doing. Ionic bonding, keep that in mind, as I said, because when we get to covalent bonding, you got to put prefixes. Okay, iron is a transition metal, so I need to figure out the charge on that. So I need to know what is the charge on PO4. Okay, that I know is 3 minus. Okay, so I'll have a total of a -6 charge, so I need a +6 charge on my cation. So the only way that can happen is that this iron has to be a +2. Okay, 3 minus and a 2, that's a 6 minus, and 3 2s, that's a 6 plus. Balance that out. So then I can write this as iron, Roman numeral 3, phosphate, or I could also use the older naming system since it's the lower oxidation state, ferrous phosphate. So iron 2 phosphate or ferrous phosphate. Titanium 4 nitrate. Remember that 4 is telling me the charge on that titanium. Okay, which means I have titanium, which is a 4 plus. And then nitrate, something we memorize is NO3 minus. Put that together. Ti, open parentheses, NO3, close parentheses, 4. Titanium 4 nitrate. Okay, let's talk about molecular substances and how we name those. Okay, binary compounds composed of 2 nonmetals are usually molecular, okay, and are named using the prefix system. We name it the same way as the ionic, except now I got to indicate how many atoms are there, using mono, di, tri, etc. There's no charges involved with molecular compounds. Okay, so we have to physically tell the reader how many is there before we can put the molecule together. Now, naming compounds and molecular, in my opinion, is easier because you're just reading what's there and writing it. Okay, or going from the name and reading what's there and writing the formula. Okay. However, one question that comes up is, why would I write something? Okay, why would I write it as NF3 or F3M? Which one would be properly written? Okay, well, what we tend to do is on the periodic table, there's a trend. On the periodic table, you got a trend for metallic compounds. Okay, where it ends up going down to the left and the bottom is the more metallic species, increasing in metallic. The more metallic species is written first by trend. So in this case, I got NF3 versus F3N. Nitrogen is more metallic than fluorine. Okay, so therefore we would not write it as F3N. We would write it as NF3. That's how we would write that formula. Now, that's not really an issue for you because typically you're either going to be given the formula, which is already written correctly with the more metallic one first, or you're given the name in words, which has already got it written correctly. Okay, so it's not an issue for writing compounds or writing formulas for you, but I just wanted to let you know why one is we put an N in front of the F in NF3 instead of writing it as F3N. The name of the compound has the elements and the order given in the formula. So as I said, that's not an issue for you. You name the first element using the exact element name, just like we did with the ionic compound. Okay, you name the cation with the name of that species in ionic. We do the same thing with the molecular. We name the second one the same way we did with the ionic compound with the IDE on it. Okay, no problem there, exactly the same. The change comes at this last statement. If there is more than one atom of any given element, you have to add prefixes, di, tri, tetra, penta, etc. to say how many atoms are there. Okay, if you don't say that, then we don't know how to put it together. Remember, your ionic compounds are your smallest whole number ratios, while your moleculars are not. So you have to give the prefixes before we can figure out how many are there in that compound. So here's an example. Okay, let's see if we can name some. Once again, I want you to think about bonding. Here, I got N2O3. What type of bonding is that? That's covalent. Got non-metal, non-metal. Therefore, I have to use prefixes. I have to tell the reader how many is there. And as I said, it's pretty well straightforward. Okay, you have to say how many nitrogens are there and how many oxygens by putting it. So we got, name it the same way we did ionic, so it'd be nitrogen, and the oxygen would be oxide. not a problem, same way. But since this is covalent bonding, I got to say how many's there, so I need to say dinitrogen trioxide. Okay, I need to say how many of each species is there. Okay, so basically 2. I need to say how many's there. Not 3, I need to say how many's there. Okay, when I write that name. SF4, okay, it's covalent bonding, so we're talking about using the prefixes here. So I have my sulfur and my fluoride, okay, but I got to say how many of each one. We don't usually put the mono, so it's just sulfur tetrafluoride. Sulfur tetrafluoride. Okay, chlorine dioxide. Okay, I say going from the words to the formula is real easy. You just read what's there. You got chlorine, I got one of them, and then I got dioxide, means 2 oxygens. So straightforward writing, ClO2. Okay, straightforward. Now I want you to realize something in this case. Notice this chlorine has INE. Everything we did up until this point has always been chloride, 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 right? IDE on the ending of it. Since this is the cation, and realistically, okay, it's not cation, but since it's the first species in the naming of your molecular compound, and we said to name the first one of the element, okay, we're going to name it chlorine, not chloride, chlorine, because it is that first species. Sulfur hexafluoride, okay, I got sulfur and I have hexa, meaning 6 fluorides, SF6. Once again, remember, we're talking about covalent bonding here. Cl2O7. Okay, so now I got to name this one. So I got the Cl, which is my first species, so that's going to be chlorine. Okay, got 2 of them, so dichlorine. And then I got oxide, and I got 7 of them, so heptaoxide. But since we got 2 vowels together, we drop the A. So we just go heptoxide. Dichlorine heptoxide. HGL, and I have the G behind it to mean that it's molecular substance. That's telling me it's a gas. That's important when we start talking about binary acids, which will be on the next slide. Okay, that little G indicates that it's a molecular substance, so I'm going to name it using molecular rules. Okay, just like we've been going through. Covalent bonding, name it. If it's an acid, I'll have AQ behind it, I'm going to name it differently. Okay, so in this case, this is hydrogen chloride. MgCl2. Okay, think about this one in the name. Now you may have a tendency at this point in time, since everything we've been doing so far has been covalent bonding, to name this magnesium dichloride. But the question is, would you be correct? And the answer would be no. Okay, that's why I said you got to think about bonding every time. What kind of bonding is MgCl2? That's ionic bonding. Okay, if it's ionic bonding, then we're just going to name the cation and the anion. Okay, so threw this one in the middle of all the rest of them. Okay, you want to think about bonding at all times, otherwise you make some mistakes as you go. Think about it. MgCl2, ionic bonding. Therefore, all I got to do is name the cation, which is magnesium, and chloride for the anion. Okay, this is not a covalent bond, so I don't need the prefixes. There's some older names that you got to be familiar with too. H2O, we don't use dihydrogen monoxide or dihydrogen oxide. We tend to call that water. Okay, NH3, ammonia, hydrogen sulfide, H2S, nitric oxide, NO, hydrazine, N2H4. These are just some common names that you're going to see. That's how we use them. So you're going to have to be familiar with those common names. Okay, so far what we've done is we talked about naming of compounds. We did molecular substances, we did ionic substances. We also got to name acids as well. There's a different naming procedure for that. Acids are traditionally defined as compounds with a potential hydrogen as the cation. For the majority of acid components and what you're going to come across in this chemistry course, we tend to start those with a hydrogen in front of it. Okay, so it's pretty easy to tell which are the acids. You may bring up a question and you say, well, doesn't water have a hydrogen in front of it? Does that mean it's an acid? Well, it can be, and we'll talk more about that as we go along in the semester. Binary acids consist of a hydrogen ion and any single anion. For example, HCl. We refer to that as hydrochloric acid, where we take the hydro, we take the stem of the word for the chlorine, and ic, the acid. Notice that we have AQ behind it. That's an indication that this is an acid. Remember in the previous slide we had HCl with a G behind it, meaning it was a molecular substance, so we named it differently. That AQ is an indication that it's an acid, and we're going to name it with these rules. Okay? If I had HBr, AQ for aqueous, it'd be hydrobromic acid. Other acids that we have to be concerned about will be the oxo acid. It's an acid containing hydrogen, oxygen, and another element. Example, HNO3. This is nitric acid. Now you might recall for the polyatomic ions, NO3 minus, nitrate. If you learn the oxyanions, okay, for your polyatomic ions, it makes an easy transition from that to your nitric acid, to your acids. Okay, let's see how we do this change. Okay, if you're talking about a per 8 ion, then what we do is we tend to change the 8 to ic. Okay, we take the 8 and we change it to ic. Okay, for example, the perchlorate ion, okay, ClO4 minus, we got perchlorate ion. Everything looks exactly the same except we take the 8 and we change it to ic when we go to the acid. Okay, you can see I got to add a hydrogen. It's got a minus charge, so I add a hydrogen to get that to balance out, so it's HClO4, and we refer to that as perchloric acid. If we have an 8 ion, okay, same thing, we take the 8 and we change it to ic. Example, nitrate ion. Got NO3 minus, we memorized that as nitrate ion. I add a hydrogen to it. Now I have HNO3. Now that's referred to as nitric acid. I have the ite ion. Okay, the difference here, instead of changing to ic, we're going to change ite to us. Okay, example, nitrite ion, NO2 minus, add the hydrogen, now to HNO2, it's nitrous acid. Nitrous acid. Hypoite ion happens the same way, except we change the ite to us, so you get hypo-us acid. Now most of them go follow these rules. There are a couple of them that actually change the name. Okay, some examples. Sulfate ion, SO42 minus, could add 2 protons to get that to balance out. Instead of just changing the 8 to the ic, we also change the word a little bit. Instead of sulfate, we go sulfuric acid. Put the old actual compound name sulfur in it, so it's sulfuric acid. Another example, phosphate ion, PO4 3 minus, 3 protons to get that to balance out. So then we get phosphoric acid. Okay, we kind of change it, put phosphoric acid. Okay. This is the naming of your oxyacids. This is for homework. Homework number 2. It has naming compounds. Be sure to work those homework problems to try to get better at naming compounds.